The next part is quite brief. So I put together a repo very recently, like today. Now it's public, so you can find it there under my GitHub. And the idea is I wanted to share two ways of working with Flower that I find them very useful, especially when you want to have many different type of data sets inside your repo that might require different configurations, for example, right? Like different data documentations if you work with speech versus images, a completely different type of models, and things like that. And also I will show how, well, maybe a lot of people know, but to explain the way I do it, the way to scale the Flower simulations. So the first part is a configuration library that is very powerful, developed by Lucas, one of my co-authors in the Fedor's paper, that we very recently open sourced in Samsung, which is called Awesome YAML. And if you have worked with other YAML config files, most of the way Awesome YAML works will look very familiar to you. But there is one or two features that I think that makes Awesome YAML super powerful and much more powerful than normal YAML files. And the thing here is as follows. And normally in FL you would start with a base config file, like maybe you have your Cypher 10 example and you are very happy with it, but then you decide, okay, now I want to consider not only this simple model, but I want a version 18, and I want also a transformer, for example. So one way of doing it is you go to your input arguments, parse, add argument, and then you need to add a new flag, things like that. And then you go to your client and you say, if model name equals ResNet 18, this code is ResNet 50, this other code. So that is fine for when you want like one option or the other, but the moment you want more options, things get completely out of control. So one way of solving it very easily with Awesome YAML is through configurations that allow you to specify how objects are being constructed directly in the config file. So for example, what I'm going to do, I'm going to share my VS Code. I think it should be here. For example, let me just go, I'm going to make this a bit bigger. So here is my base config file that is something that is very standard. And well, by the way, something I haven't said is that this code is exactly the same as the Flower simulation example, but I have changed it slightly so it works with this Awesome YAML library. So let's look at this first. So we have our model, and then there is a property that we call build, and this is a bind node, which means that it's going to build an object, it's going to build it, which is this object. It's going to build it only when you tell it to do so in the code. So for example, if we go to source models.net, that is source model, my file, and then .net is here. So this is the standard model we have in the Flower simulation example. And okay, I have this here. How does it work? So for example, if I have my standard Flower client, I'm passing a new argument, which is a config, which in this case is this config. And I will say, oh, config.model.build, and you call it, and this will be equivalent to if you were, here importing from models, import.net, and here you just put .net. That would be equivalent. Let's say if we want to do something a bit more sophisticated, for example, let's say we want to consider a new optimizer. We could have what I said before. If optimizer name equals SGD, do this. Atom, do that. But with Awesome YAML, you can make in a much cleaner and I would say versatile way. For example, in this case, you can see the config.optim is calling something.
I don't understand. I see that.
Oh, sorry. And then what what is doing this config optim is coming here. It has the client config and is instantiating torch optim SGT with these hyperparameters. But we know that when we instantiate our optimizer, it still needs you to pass the parameters. So you can still do that in the code. And the thing is that this process is common to all optimizers. So we can leave that there. Let's say now I want to change this. I don't want SGD. I want to try. So you can do a new config, for example, like this one that inherits from your base config, and you only change that node in the config that has to do with the optimizer base atom and you learning it. And this config runs everything exactly as your base config with only this change. Only the atom optimizer in the client has been changed. And you can imagine how this can be extended to different situations. For example, let's say now I don't want my tiny model we saw here of in nets. I want a ResNet 18, which is a very common baseline model. You can do this through a config. Again, to rewrite everything, you just read. You rewrite what needs to be changed from the base. And similarly with other nodes. For example, here we have a bigger model. Maybe we want to use GPUs, whereas before we were only using CPU to train the clients. So this is one of the things I wanted to share. Library is it's super versatile, and I now use it everywhere. So if someone sometimes struggles with config files or things get out of control with hundreds of config files, I think this is could be one solution. The other thing I wanted to share is Flower simulation. I think most of you or all of you know that there is this, you can run Flower like for real with real devices, or you can run it in simulation mode, which might be more appropriate if you want to just run large scale experiments. And that works right out of the box. What I want to show in these slides is how you can run the simulation, not in just a single computer, but in multiple computers that are in the same network. And the process is actually super easy. So you need to meet two conditions. One is that all the nodes have to be visible to each other. They have to be in the same network. And the other one is that every node has to have exactly the same Python version and the same repository, like your repo, your code, and your environment has to be the same. And then you would, for example, go to whichever node you want it to be the head of the node, and you type the command you see there, ray start -- head, and it will print something automatically for you. And you will see some steps there, which I have put in a red rectangle. To connect this RAID runtime to run this command. So you will go to another node, type the command, I'm doing it there, press enter, and then you can completely forget about that node. You don't need to run anything at all. Everything will be done for you under the hood. Then you go back to the head node, and you can write, for example, ray status. And if you do so, you will see a summary of all your resources. In this case, I can see I have 2 nodes. And because I ran this on 8 GPUs, I can see that the total I have is 16 GPUs, which is expected. Okay, now we have created this ray cluster, which is what Flower the hood function. How can I make all my clients to be distributed to all the GPUs in this multi setup? So you would just launch your experiment as normal from the head node. So you will go Python main.py, blah, 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 and Flower will schedule the clients wherever there are free resources. And this depends on the resources. You are telling your clients that depending on the resources Flower thinks the clients need. In the example I have put together in the repo, you do this by So you have to do the ray start head, the ray start, and then passing the IP from a node. But at the end, you can run this example just passing dash dash attach, and everything will be done for you. So I think this is one of the great features in Flower simulation, that you can scale very easily to multiple machines. And these machines, they don't have to be GPU machines. They can be anything. You can have your laptop and another desktop you have at home. That will work as well.